stage is yours.
Okay, thanks. So my name is Bebon. I'm a PhD student in Thomas Speck Group in Stuttgart. And today I basically want to extend his talk. So I'll also talk about the thermodynamics of active matter, but I'll also show you how we can apply the concepts he talked about earlier to larger length scales. So look at macroscopic systems and collective behavior. So I guess by now it's established that active matter is by construction, active systems are by construction out of equilibrium, because the defining trait of an active particle or an active agent is that it uses it locally converts energy that is stored in some sort of fuel into some sort of functionality. So for the sake of my talk, this will be directed motion. So I'll focus on directed active, motile active matter. And of course, we all know that this energy cannot just vanish into thin air, so it will have to be dissipated by each particle individually into its surrounding medium. So today I will show you how we can calculate the exact dissipation rate and therefore the entropy production rate of such active colloidal particles, and then building on these results also show you how turn towards larger length scales and show you how these local effects manifest if we look at the collective behavior of macroscopic many-body interacting active particle systems. So to do this, I want to take you on a very quick journey through different length scales. So I just cover some of the, quickly cover some of the results Thomas already talked about for the microscopic model, and then I'll show you how we go to a mesoscopic description. And then I'll show you how we can use this mesoscopic description to further cross-grain into an effective field theory, where we have hydrodynamic, smoothly varying order parameter fields. And just as a note, one can also go the final step towards a scalar field theory, but unfortunately, I won't have time to show this today. All right, so let's get started. So on the microscopic scale, it's the same model Thomas already introduced earlier. So we are looking at a very simple thermodynamically consistent model for a catalytically propelled particle, where we have a single colloidal particle submerged in an ideal solute, where we differentiate between substrate and product. And then this colloid, it has a catalytically active zone here in this shaded region, where if a substrate enters, it can be converted to a product and vice versa, where this set of rates satisfies detailed balance. And then the system is driven out of thermal equilibrium by an external chemostat that constantly drives the conversion between substrate and product, and therefore constantly injects energy into our system. And what we see from simulations and also analytical calculations is that this is already sufficient to observe directed motion. So there's no hydrodynamics involved at all. It's really just particle pairwise interactions between these solute particles and the colloidal particle. And the average propulsion speed of the particle can be written in this very nice and concise form, where lambda is a microscopic length scale, and this calligraphic J describes the flux between solute reservoirs. So this calligraphic J essentially gives you the rate at which you have a conversion from a substrate to a product molecule, and then for every successful reaction, you displace the particle by a small distance lambda along its orientation, which then constitutes on average the speed V0. And the main insight you can learn from looking at this simple microscopic model is that you actually don't need to track all the explicit degrees of freedom of the solute molecules, but you can condense them down into only two effective parameters, which have a very clear physical interpretation. So the first one I already told you is this small length scale lambda, and the second one is an effective attempt rate. So this basically just characterizes the rate at which these conversions occur. And in building on this, you can drastically reduce the complexity of your system and enter this mesoscopic description, where you have catalytic particles that undergo effective chemical events. So we have our catalytic particles. We no longer resolve the solute degrees of freedom, and with a given rate, Ki plus, it converts essentially a substrate to a product, and in turn is displaced by this small distance lambda along the orientation. And of course, the reverse reaction can also occur. And if you write down the equation of the evolution equation for the system, you will see that these chemical events constitute a second current to your system, which we will call the chemical current. And tracking this chemical current then allows you to keep track of the underlying solute dynamics or the details of the solute dynamics you require to calculate the actual dissipation rate of your system. And a convenient thing about this model that Thomas already mentioned is that if we look at the small lambda limit, so if this displacement is small compared to the size of the catalytic particle, we immediately recover the standard evolution equations for active Brownian particles, which we now enhance by this additional thermodynamic information, which is encoded in this chemical current. So now we can just use the standard framework of stochastic thermodynamics to immediately write down the mean steady state dissipation rate for such a system. So let me remind you, it's not just one particle now, but n particles. So this is why we have the sum here. And then the dissipation rate, the average dissipation rate is then just given by the sum of products between currents and affinities. So the first current here is just a particle current due to translational diffusion and the forces that are acting on the particles. And the second one is this chemical current due to these effective chemicals. And if you do the math, you'll quickly find out that most of the terms cancel, and the only one that remains is this chemical current times the chemical potential difference. So this is just the chemical potential difference between the solute reservoirs. So what this tells you is that the dissipation is only determined by these effective chemical events, and you can then also write it in a more concise way, maybe by identifying the solute flux again. So you see here that this is the rate at which these conversions happen. For every conversion, you use up delta mu. So what this describes here is just the rate at which you inject work into your system. And by first law, it's equal to the dissipation rate, which we recover here. And let me emphasize one point here. So if I give you the explicit expression for the chemical current, you'll see that we have here this chemical mobility and this chemical diffusion coefficient, which directly depend on these underlying solute dynamics, depends on the underlying solute dynamics through these two effective parameters. So you have here this lambda squared kf, which are exactly these two parameters I introduced earlier. So what this tells you is that if you want to calculate or recover the actual dissipation rate or the entropy production in a thermodynamic sense of active Brownian particles, you kind of have to consider some sort of detail that underlies the self-propulsion mechanism, which in our case are these catalytic reactions. All right, so up until this point, I've mostly talked about particle resolved descriptions. So we could still resolve the position and orientations of individual particles. And for the rest of my talk, I want to go one step further by cross-training the dynamics to fields. And without going into much detail here, I'll just give you a sketch of what we are doing. So the basic idea is that we integrate out degrees of freedom we are no longer interested in, and then identify order parameter fields as moments of particle orientation. So what this ends up in is an infinite hierarchy of coupled partial differential equations. So we get for the 0th moment is just the particle density with a simple continuity equation. First moment is the polarization, and then so on. So what this does is essentially we can now describe the dynamics of our system in terms of these hydrodynamic fields. And then building on the result we got for the mesoscopic system for the dissipation rate, we can also express the dissipation in terms of these hydrodynamic fields. And if we do this, we immediately find that the dissipation rate is once more just given by the solute flux times the chemical potential difference, where now the solute flux depends on these hydrodynamic fields. So we have this particle density here and the polarization field. And as we've seen before, this solute flux still depends on the explicit solute degrees of freedom through this chemical mobility here. Another major benefit of the systematic bottom-up construction that I've shown you is that we can identify an unambiguous local dissipation rate. So this is this k dot, that is small q dot here. And this gives you a position resolved dissipation rate field, which can give you a lot of information about your system, especially how it reacts to local, how the dissipation reacts to local features. So think, for example, about some kind of confinement or some kind of obstacle. So what this can tell you is now how the system's dissipation reacts to this confinement or this obstacle. And for this, I want to show you, for the last few minutes, I want to show you an explicit example where we can calculate this local dissipation rate. And that would be just standard active Brownian particles undergoing motility-induced phase separation. So I guess most of you are familiar. So on the left here, you just see a simulation snapshot of a few thousand active Brownian particles. And we know that if the density is sufficiently high and particles move sufficiently fast, they will undergo phase separation and phase separate into a dense liquid and a dense liquid cluster and a gaseous background. And if you have a time trace that is sufficiently long, you can average and obtain these effective hydrodynamic fields. So the color here is just the density, and as unsurprisingly, the density is highest in the cluster center. and then the arrows indicate the polarization field, and you see that particles tend to polarly align along the interface and point inwards. So with this, we can now immediately calculate the dissipation rate, and what we find is that the dissipation rate closely resembles the density field, which is probably unsurprising for most of you, because wherever particles are present, they will use up energy, they will dissipate energy, and if particle density is higher, this dissipation rate will just increase. And because particle density is highest in the cluster, the dissipation rate is highest in the cluster as well. So this tells us that this first term here, which is essentially in housekeeping terms, so wherever particles are present, they will dissipate a certain amount of energy, is the dominant contribution to the dissipation rate. An interesting insight is when you subtract this housekeeping term now. So what you get is something that looks like this. So you have this ring along the interface between the cluster and the gas. But however, note that all of the values that I've shown here are negative. So what this tells you is that the local polar order along the interface between cluster and gas actually locally reduces the dissipation. However, I should also mention that if you look at compare the length scales here, or compare the scales here, you will see that the housekeeping contribution has like 3 orders of magnitude larger than all of these intricacies that come to local polar order. And I guess with that, I'm already at the end of my talk. So I hope that I was able to convince you that dissipation, irrespective of the length scale you're looking at, will always depend in some way on the microscopic details that lead to the activity. And yeah, with that, I want to thank you for your attention and also thank the organizers for the opportunity to speak here.